Hello everybody, this is Rudra here. Welcome to BMD lecture series. Today we will continue with prescriptive analytics and that too coverage on linear programming problem. And in the last lecture we have already discussed about this particular structure, and the typical linear programming structure is like this. We have a objective function, we have a constants and we have condition, and then we are looking for the optimum solution for a particular business problem. So, that means if you summarize, then we have the kind of structure like objective, then issue about the decision variables, constants, parameters, non-negativity. So, that is how the modeling structure altogether. And in fact, so let me give you the kind of structure here. Okay, so okay, so this is how the particular issue. So, we have objective functions and we have issues about the decision variables, constants, parameters and non-negativity. So, now in order to simplify the particular or we like to understand in a more attractive way. So, let us start with like this optimize a z equal to c x subject to x less than equal to b and x greater than equal to 0. So, this is how the simple LP structure, and let us say x is the x consists of two variables x 1 and x 2, that is the requirement of decision variables, and accordingly the problem can be analyzed like this. So, z equal to c 1 x 1 plus c 2 x 2 subject to a 1 x 1 plus a 1 2 x 2 less than equal to b 1 and a 2 1 x 1 plus a 2 2 x 2 less than equal to b 2, and then x 1 greater than equal to 0 and x 2 greater than equal to 0. So, this is how the kind of LP structure, and that too with respect to two variables. So, that means we need actually linear combination of these two variables, that too with respect to objective functions. Obviously, this is with respect to optimization z, and the optimization structure may be maximization type or the kind of minimization type, and the constants can be of three types. It can be a less than type, it can be greater than type, or it may be equality type. So, that means we have a objective functions which can be either maximization type or minimization type, then subject to constants, and some of the constants are greater than type, some of the constant less than type, and some of the constants may be equality type. Now, knowing the particular situations, then you will search for the optimum solutions. Sometimes the problem will be more complicated, like we have objective function with several constants, where some of the constant will be less than type, some of the constant will be greater than type, and some of the constant will be equality type. So, that means technically we have a two kind of situations. For instance, let us say we start with optimizing a particular objective functions where z equal to c 1 x 1 c 2 x 2, and then all the constants in generals or as per a kind of simple structure corresponding to objective function maximization type, the constant should be less than type. And on the other side, if the objective function is the minimization type, then the constants must be greater than type. So, now the usual structure or simplest structure is like this. When the objective function is, that means technically in this context, if I put maximizing z equal to c x c 1 x 1 plus c 2 x 2, then the first constant should be less than type, second constant should be less than type. Again, so in the kind of minimization problem, so we can write like this: minimization of z equal to C1 x 1 plus C2 x 2 subject to same A1 1 x 1 plus A1 2 x 2, then it can be greater than equal to B1, and then A2 1 x 1 plus A2 2 x 2 greater than equal to B2, and then x 1 greater than equal to 0 and x 2 greater than equal to 0. So, this is the kind of structure called as minimization structures. In the kind of minimization structure, and that too in the simplest way, corresponding to objective functions, the constant should be greater than type, and corresponding to the maximization problem where the objective function is maximization type, then the constant should be less than type. If that is the case, then this is a simple way of LP structure, and it is very easy to solve this kind of problems, like maximizing z with the less than constant, and minimizing z with objective function with respect to greater than kind of situation constants. So, now in reality you will find the objective function may be maximization type or minimization types, where the constants is like that, some are less than type, some are greater than type, and some may be equality type. So, that is a kind of complex kind of situations and complex kind of environment where the problem will be more interesting, and then it may be more challenging, and then we need some kind of analytic structure to solve the problems as per the particular business requirement or the management requirement. Of course, whether it is the kind of situation like all are less than type or greater than type corresponding to maximization situation, minimization situation, then we need not require extra kind of structure through which you can simplify the problem and looking for the values of the decision variable. But in reality, if objective function is maximization or minimizations, and then the constant will be the kind of mixture like less than, greater than, and equality. So, we have a kind of system through which corresponding to a particular objective function maximization, then all the constants can be transferred into less than type, again corresponding to minimization problems. So, the constants can be transferred into greater than type. So, we have a kind of system through which we can do that first, then we look for the kind of solution, that is the optimum solution. So, that means we are here in the kind of business analytics, we like to address how it can be done, how we have to structure, restructure, through which you can actually easily generalize the problem, and then look for the optimality and get the values of the decision variable through which you can address the business problem more effectively. So, that means knowing all these structures and kind of algorithms through which actually you can analyze the problem more effectively, and then looking for the kind of optimality through which you can actually generalize the problems, and then you can go for the kind of management decision. So, to know all these things, then we start like this. So, here the structure is like this. What we can say that the kind of components. So, 5 components which we have in the kind of LP structure, that is the objective, decision variable, constants, and the kind of parameters which we have already highlighted here, C1, C2, A1, 1, A1, 2, A2, 1, A2, 2. So, these are, and B1, B2, these are the kind of parameters, and then the decision variables are x1 and x2, and then the constant is nothing but the first constant and second constants, and the non-negativity. So, that is actually the kind of what we can call as model structure. So, that means if I like to address this one, so I can simply put like this, let us say maximizing z equal to Cx and x less than equal to b, x greater than equal to 0. So, that means here, so C, A, B are the kind of parameters, and then objective is nothing but the entire functions, and so far as a constants are concerned. So, this is in a vector format. So, x less than b equal to is a kind of constant, and then non-negativity is nothing but x greater than equal to 0. So, that means corresponding to the kind of LP structure, you have to transfer the problem into this particular format, depending upon the situation, depending upon the kind of requirement, depending upon the kind of business problem kind of issues. Then finally, we look for the kind of optimum solution. So, that means the whole idea is understanding the problems, you have to first transfer the problem into the particular model structure, LP structure, and then we think about the kind of optimum solutions as per the particular business requirement. And while doing the kind of model formulation and the kind of solution, and that is the looking for the optimality of the kind of solution, that is the values of the decision variable. So, we have a kind of some kind of assumption we like to cite, and then on the basis of that particular structure. So, we like to have the optimum solution, and some of the assumptions which can be usually connected with the LP structure is nothing but proportionality, additivity, divisibility, and certainty, and these are all called for model validations. So, like we have already discussed in the case of predictive analytics. So, here also a similar kind of structure. So, we have the kind of problem, develop the model, then look for the solution and validate the models as per the particular requirement. That means, the validation is here once you get the values of the decision variables. So, at least the decision variable should satisfy the particular constants. If that is not the case, then we cannot call it optimality, and the values of the decision variables may not address the problem as per the particular requirement and the kind of effectiveness. So, so we like to look for the solution which can address both in the kind of objective function and the kind of constant. So, that means technically we must have a situation where the values of the decision variables can be obtained, where we can optimize the objective function, and the constants can be satisfied equally. And once you set all these things and develop the kind of structure or develop the kind of algorithm by default. So, once you get the values of the decision variables, so that will be automatically streamlined. So, that means the constants will be satisfied and the objectives can be also fulfilled, and then we can actually easily address the business problems as per the particular business requirement. So, now looking for this particular structure. So, let's move how is the LP structures, and then the formulation of LP model is like this, and define the decision variables, determine the objective functions, identify the constants, and determine appropriate values for parameters, and determine whether an upper limit, lower limit or equality is called for, and use this information to build a model and then validate the models. Like what we have already discussed here. So, corresponding to this particular LP structure. So, this is how the formulation requirement. So, decision variables to be defined properly, and then fix the objective, whether it is a single objective or multiple objective, and then and that will be addressed with kind of linear combination structures, like which we have already highlighted with respect to two variables. So, the maximization of z or minimization of z is nothing but C1 x1 plus C2 x2. So, that means that is the kind of linear combination. So, that means we like to know what is the optimum combination or linear combination through which actually you can generalize the problem, and then analyze the problem or address the problem in such a way the business objective can be effectively addressed as per the particular requirement. So, likewise constants can be satisfied, then all the parameters and the kind of limit, the kind of structures need to be actually fulfilled. So, accordingly, so we can address the problem. So, we start with a simple structure like this. So, let us say this is a simple linear programming problem with it two variables, and the problem will be like this a business firm that assembles computers and computer equipment is about to start production of 2 new web server models, and each type of model will require assembly time and inspection time and storage space, and the amounts of each of these resources that can be used to the production of the servers is limited, and the manager of the business firm would like to determine the quantity of each model to produce, so that we can maximize the profit generated by the sales of these servers. So, that means this is a production problem again with respect to 2 variables, that to web server that to actually 2 web server models, and the values of the decision variables will be represented as x1 and x2. So, accordingly, so you see here, so this is what x1 the quantity of server model to produce, and x2 is the quantity of server model to produce. So, that means we have 2 models, model 1 and model 2, that is now here the kind of output of this particular business, that is the component through which actually the entire operation will be looking for. And so, let us assume x1 is the kind of first decision variable, and x2 is the second decision variables, and x1 represents the quantity of server model 1 to produce, and x2 is the quantity of server model to produce. So, then we need actually the LP formulations, and this is how the beginning where x1 is defined and x2 is the defined, and this is a kind of production structures, and that too with respect to 2 variables. So, obviously, LP structure will be what should be the objective function, and what are the constants through which you can address the typical problem. So, now for that, so we need actually additional information. So, now the additional information is here. In order to develop suitable model of the problem, the manager with design and manufacturing connect with design and manufacturing kind of department. As a result of these structures, so the streamlined of the process will be like this. So, this is the type 1 structure and type 2 structure, that means corresponding to model 1 and model 2, and since profit is the prime goal of this kind of business, and that too that too we we are actually more interested, and in fact the entire prescriptive analytic structure will be like that. So, obviously, profit is the prime goal. So, the objective will be the profit function, and here the business firm manager actually wanted that there should be at least $60 profit from the type 1 and $50 profit from the type 2, and accordingly, so this is actually 60 and 50. Accordingly, there are 3 constants, the assembly part, then inspection part, and the storage space. So, now this is actually type 1 which we represented x1s, and here type 2 which represented x2. So, now corresponding to the objective function. So, now this is actually objective function parameter coefficient, and this is objective function parameter coefficient for x2. So, obviously, so the z can be 60 x1s and then plus 50 x2. So, accordingly, so it is formulated here. So, maximize z equal to 60 x1 plus 50 x2 and subject to constraints. So, the constraints are here, there are 3 constraints. So, first constraint is the assembly part, and that too 4 hours required for model 1s and then 10 hours required for model 2. So, that means when they will go to the assembly department, so the product 1s needs 4 hours and product 2 needs actually 10 hours. So, obviously, so the first constraints will be 4 x1 plus 10 x2. So, now we look for the kind of research constraints and how much total hours actually available in this particular department. That means, again we need additional information. So, this is the part of the additional information, that to the right side of the particular right side information about the particular constant. So, that means technically, so we have a system called as z equal to Cx and x less than equal to b and x greater than equal to 0. So, that means we need the A coefficients, and we need the information about the C coefficient, and we need the coefficient about B. So, accordingly, so since there are two products, so C becomes C1 plus C1 and C2. So, accordingly, C1 equal to 60 and C2 equal to 50, and again, so there are three constants. So, obviously, so A11 plus A12, A11 x1 plus A12 x2, A21 x1, A12 x2, then A31 x1 and A32 x2. So, these are the three constants. So, that means technically we need again the coefficients of these coefficients. So, accordingly, so the coefficients are here. So, the first second constants, that is the inspection. So, it needs actually 2 hours in the first product and then 1 hour for the second product. So, obviously, the second constants will be 2 x 1 plus x 2. Again we look for the resource availability, and then again so we go for the second information base. Here actually inspection time, so maximum availability of your hour is 22. So, obviously, this will be a 22, and then third constant will be the storage space, and for that 3 units for type 1 and 3 units for type 2 accordingly. So, the left hand side of the constant will be 3 x 1 plus 3 x 2, and then how much availability. So, storage space availability is actually 39. So, we put actually here less than equal to 39. That means, whatever availability here. So, these are maximum availability. So, that is how we need actually optimization. So, resource optimization means with a maximum limit and as per the requirement and as per the kind of combination. So, we look for the kind of exact structure through which everything can be satisfied equally. Then the business can be reached to a particular situation where that can be addressed more effectively. So, now corresponding to this problem. So, if you see here, so this is what the the problem base, and the understanding the problem base, we transfer the entire problem into simple LP model like this. So, that means we have actually a big information or pool of informations with respect to the problem details, the kind of requirement, the kind of structure, the kind of availability, and the kind of objectives, and the kind of constants. So, all these things will be simply transferred into a model format. So, now the model is ready to operate. So, now once the model is ready, so then we will look for the kind of solution. This is how the first and choice of the particular situation. So, let us see how is the kind of structure through which you can actually move. So, for that we can actually go for the kind of solution, and so here the since it is actually a bivariate structure, that is with respect to two variables, that means here our objective is a maximization type, and that too for two variables, and according to the problem structure the objective function is the maximizing z equal to 60 x 1 and 50 x 2 subject to three constants for x 1 plus 10 x 2 less than equal to 100, and 2 x 1 plus x 2 less than equal to 22, and then 3 x 1 plus 3 x 2 less than equal to 39, and then x 1 and x 2 greater than equal to 0, because it is the kind of production kind of issue, and obviously. So, the values of the decision variable can be either 0 or it can be positive, it can no way it can be actually a negative. So, as a result, having the kind of structuring, the kind of requirement. So, now we like to optimize the process through which we like to know what is the exact values of the decision variable through which the business firm can reach the optimum profit subject to the available constants or the kind of available resource base. So, accordingly we can move, and what we can actually address here, since it is with respect to two variables. So, now you can have actually the solution graphically as well as algebraic way. So, now let us see how graphically can be analyzed, because graphically give you more accurate way to understand. Those who are beginners, they can easily can pick up how it is actually the kind of structure of the prescriptive analytics, that to the linear programming framework. So that we can actually address and then look for the kind of optimality. So, that means actually the way we like to highlight here now. So, we like to create a kind of flexible environment, that means the kind of various alternatives, because it is the kind of best combinations. So, what should be the x 1 pool and what should be the x 2 pool. So, that objective function can be at the highest level subject to satisfaction of the kind of constraints. So, that means it cannot be actually the kind of unique kind of structure through which you are looking for the decisions. So, since it is a kind of decision making process, so obviously we must have some kind of alternatives. Now, here the kind of alternative is the kind of different combinations, and that too with respect to x 1 and x 2. So, we must have at least two different flexible structure. As a result, we can think about the process, and then we take the decision. If it is only one kind of situation, then there is no need to take a kind of no need to take a kind of decision. So, since actually there are more than one kind of situation, so there is a need of decision which one should be finally taken into consideration, and that too you have to take care of the kind of objective issue and the kind of constraint issue. So, obviously, so the whole idea is that graphically we see how is the kind of structuring. That means, we simply streamline the process slowly, then we finally freeze where the kind of optimality can help us to analyze the problem, and then address the business issue more effectively as per the particular requirement. So, now so far as graphical solution is concerned. So, what we will do actually? So, we like to visualize with respect to x 1 and x 2, and then we simply put the constant as per the particular requirement, and then we like to fix a kind of boundary, and through which actually the resource base can be adjusted. That means, it is actually a question of optimal allocation of resources, since it is a kind of production process. So, the simple understanding or theoretical structuring is like this: what should be the optimum production combinations, and that too with respect to available resource available resources, right. So, that means technically, so how these resources are allocated optimally, so that the particular production combination will be more effective or more accurate. As a result, the profit of the business firm is at the highest level. That is what the actual agenda and the kind of requirement in this particular structure, and that too for the prescriptive analytics structure. So, now in the first, there are 3 steps altogether. In the first step, so plot each of the constants, and then check the kind of since it is a kind of linear programming problem, obviously all the constants are in a kind of linear format only, and since it is with respect to 2 variables, then obviously with a particular constant we can have a kind of straight line, and then we can check the kind of feasibility. For instance, in a kind of linear programming problems corresponding to a particular objective, so the constant should be less than type or greater than type. So, the first and the requirement of the graphic structure is make the constant into equality, then find out the points for both the kind of structure as per the particular equation. Then you draw the line, and then we allow, or you can actually apply the kind of a reality. So, whether it is a less than type or greater than type. For instance, let us have a kind of structure here. So, for instance, here the constant is 4 x 1 plus 10 x 2. So, that means first of all what will you do? So, we can write here simply the kind of requirement. So, for x 1 plus 10 x 2 means, so it will be like this, for x 1 plus 10 x 2 equal to simply 100. So, now this is a straight line equation, and so the how you have to draw the straight lines corresponding to the graphical requirement. So, just put x 1 equal to 0, then find out x 2 value, and then again put x 2 equal to 0, find out x 1 value. So, that means, so we need actually two different point to have a straight line. Then once you have the straight line, then after that you can apply the actual requirement, whether it is a less than type or greater than type. For instance, so here putting x 1 equal to 0, x 1 equal to 0, x 2 equal to simply 10. So, so x 2 equal to 100 by 10. So, it is 10. Again putting x 2 equal to 0, x 2 equal to 0, x 1 equal to 100 by 4, that is 25. So, that means technically we have two different points. So, one point is 0 10 and another point is 25 and 0. So, now so the structure will be like this, you simply go to the particular structure like this, and then so this is x 1 and this is x 2, and then corresponding to x 1 0. So, x 2 will be 10. So, let us assume that somewhere here, and then again putting actually a x 2 equal to 0, x 1 equal to 25, let us somewhere here. So, that means it will be in the x 1 line only, and corresponding to the first ones it will be on the x 2 line only. So, now we have a two different corner point, and just join the particular point. So, this is how the line is all about. And then so the first step of this process is make the constant into equality, and then have two different points, so that you can draw a straight line. After drawing the straight line, so then you look for the kind of actual actual fact, that is the actual reality. So, whether it is a less than type or greater than type. Since it is a less than type, by default the resource allocation will be only in the left hand side only. So, right hand side will not be possible, because that is the availability of resources only, that is the maximum availability. So, that means we may be here, so we may be here, so we may be here, so we may be here. So, these are the this line will give you the upper limit, and then we have a lots of interesting area here, and the solution will be within this particular area somewhere maybe up here, maybe here like this. So, it depends upon actually combination of other constant altogether. So, like for the first constant, the structure will be like this. Again you go for the second constant, that is 2 x 1 plus x 2 less than equal to 22. So, the first step of this process again is 2 x 1 plus x 2 equal to 22. Then again look for two different points, draw the lines, and then again allow the actual fact, then that is the less than type. So, you put the less than type, then by default you will get the kind of the actual zone. And now the second constant will be applied like this. So, for instance, here if you put x 1 equal to 0, x 2 equal to 22. So, that means somewhere here, and then if you put actually x 2 equal to 0, x 1 equal to 11. So, let us assume somewhere here. So, the line will be like this. Again, since it is less than type, so the zone will be this side. Then come to the third kind of constant. This is 3 x 1 plus 3 x 2 less than 39. So, put x 1 equal to 0, x 2 equal to 13, and that to somewhere here somewhere here, and then again put x 2 equal to 0, then x 1 equal to 13, and accordingly. So, it will be somewhere here. So, you now join these 2 points. Okay. So, this is 11. So, it will be like this. Okay. So, now so we have here these are all zones less than zones. So, that means technically, so this is the first constant, this is the second constant, and this is the third constant, and then these are the typical zone here. So, now having this typical zones, so we have actually different extreme points, and these extreme points can be the possible solutions. These are all called as technically corner points, and taking care of all the constants and simultaneously it will give you the the kind of feasible zones, or bounded bounded kind of structure, and then the boundary we look for the extreme points, and these are all called as corner points. So, now these corner points are the possible solutions, that is the possible solution means that is the optimal solution for the particular business problem, and out of all the corner points one particular corner point will give you the optimum solution. This is what the basic structure of LP, and now in order to know the particular fact, so let us go to the kind of structure. So this is what the graphic structure. So we look for optimal solutions, and we look for feasible solution space, then corner point solution, and then a redundant constant. So that means we have actually couple of constants. So while operating the particular process and looking for the optimality by integrating all the constants simultaneously, depending upon the kind of constant actual structure, some of the constant may not be operative in the kind of final requirement. Then we have a kind of slack structure and surplus structure through which you can understand the particular requirement. So technically, so this is what the kind of game. So whatever I have already mentioned. So this is the first constants, and this is the second constant. So now if you omit actually the third constant, still we can get the particular solutions for this case. So this is a kind of solution corner point, and this is a kind of corner point, and this is a kind of corner point, and this is a kind of corner point. So that means with respect to two constants, so we can have a kind of feasible structure, and that too the boundary will be like this, and we have 4 different corner points, and one of such corner points will be give you the optimum solution. In fact, if you have only one constant, still let us say this is only one constant, then we have 3 corner point 1, 2 and 3. Suppose we will take this particular constant only, then by default we have a 3 corner points again. So that means if you take only one constant, we have a 3 different flexibility. If you take the second constant only, then still we have a 3 different corner points. Of course, the x1 position and x2 position will be different, but still we have a kind of flexibility to find out or to take the decision which one should be the final choice to optimize the profit subject to the particular available resources. And again, so when we add another constant, then the count of the kind of feasibility zone will be slightly restricted, because the entire structure is like that. When we add one after another constant, then the kind of feasible structure or feasible zone will be restricted slowly. So like in the case of predictive analytics, what we have already discussed, when you go one after another variable, then obviously the kind of the problem complexity will start increasing, and then and there are lots of additional problems will be coming up, and then finally we look for the solution after addressing all the problems simultaneously. And similarly, this is also case if you add one after another structure, then it will be giving you some kind of complexity. So let us start with the kind of structure here. So having the kind of structure, so let us go to the third constant. So this is actually the third constant, and now this is what the okay. So this is what the third constant, and so initially we have the kind of structure here like this, and so this is the first constant, and this is the second constant, and then finally we have the third constant. So now obviously, so this is the final zone. So that means taking care of all the three kind of constants, then finally you have one corner point here, you have another corner point here, we have another corner point here, we have another corner point here, and we have another corner. That means, with respect to one constant we have a 3 flexibility, with respect to means out of 3 constant, if you go one by one, then every times you have a 3 flexible positions. So, now if you add up 2 simultaneously, taking if you do not consider this particular constant, then again we have 1, 2, 3 4 different situations. Similarly, if you remove these ones, then still we have a 1, 2, 3, 4. So, we have a different kind of combinations. Now, having all the constants simultaneously, so altogether we have a 5 different corner points. Then the optimum solution will be at a particular corner point. So, that is how we are actually looking for and searching for this particular requirement. So, now what will you do? So, again you go to the particular structure and check how is the final solution, and the particular structure is called as actually the extreme point structures. You can call as extreme points or corner points, and through which you actually some of the particular optimum solution will be lying. That means, technically out of all these corner points, one particular corner point will give you the optimum solutions, and that is how what will you do. So, we take all the corner points, that is with respect to the combination of x 1 and x 2, and put these value in the objective functions, and check where the values of the objective function will be at the highest. So, once you get, then accordingly we can actually look for the solution, and then we can fix which one is the optimum solution out of all possible alternatives. So, it is clearly like the kind of predictive structures earlier we have discussed. That means if you change a different kind of structure, we have actually flexible options, and then we have to pick up a final one which can actually finally address the problem more effectively. And the entire business analytics structure is like that. We like to choose a particular technique corresponding to a particular problem, or the corresponding to the problem if you on data or data availability, where actually the kind of situation is like that. We have to pick up a best out of the several alternatives, and then that particular best requirement will address the problem more effectively. So, that is how whether you are in the predictive analytics or prescriptive analytics, the whole idea or the the kind of simple message is that we like to bring a kind of flexible structure through which we can pick up a kind of requirement which can effectively address the business problems, and then we can do the kind of management decision as per the particular business requirement. So, that means that is the beauty of this analytics. So, the one of the challenges how many alternatives you can bring within a kind of particular problem with different kind of constant and situations, or the kind of diagnostics and the kind of sensitivity structure through which we can actually analyze the problem more effectively, and then look for the kind of solution as per the particular business requirement. So, with this we will stop here, and in the next class we will continue here to get the means we will look for the search of the optimality in a kind of effective way as per the particular business requirement. Thank you very much. Have a nice day.